1 minute ago, scientists inside a closed-door meeting in Rome reclassified Campi Flegrei from a monitored volcano to a national security threat. The data on the screens showed something they'd never seen before. Ground beneath nearly 1 million people is fracturing toward explosive failure. Is this Europe's first supervolcano awakening in real time? Could pressure release safely, or is detonation inevitable? And could evacuation ever succeed with only hours of warning? At 4:37 this morning, senior scientists from Italy's National Institute of Geophysics and Volcanology entered a secure conference room in Rome. No media, no public announcement, just raw data projected onto monitors showing seismic patterns that matched nothing in the historical record. By 6:15, Campi Flegrei had been officially reclassified. The decision was unanimous. This volcano, dormant for nearly 5 centuries, now carries the same designation reserved for nuclear facilities and critical infrastructure. The threat isn't theoretical anymore. The reclassification means continuous satellite surveillance, emergency protocols activated across Naples, and a quiet acknowledgement that traditional hazard planning may be insufficient for what's building beneath the surface. But this was only the first warning. Campi Flegrei doesn't behave like other volcanoes. Mount Etna sends lava flows you can track. Icelandic systems give weeks of detectable signals. But Campi Flegrei operates as a sealed pressure cooker, a 13-kilometer-wide caldera hiding beneath neighborhoods, highways, and ancient ruins west of Naples. There's no towering peak to watch, no obvious vent to monitor. The system is fundamentally different. Instead of releasing pressure gradually through eruptions, Campi Flegrei's thick cap rock traps magma and volcanic gases below the surface. Every tremor, every cubic meter of rising ground adds stress to a crust already stretched nearly to breaking. Warning times won't be measured in weeks or months. One scientist predicts hours at most. The population density makes it worse. Nearly 900,000 people live directly above the caldera's fractured floor. Another 6 million occupy the greater Naples region within reach of pyroclastic flows. Dense urbanization covers the entire red zone with apartment blocks, schools, fuel depots, and port facilities. Most residents have no idea they're positioned over what scientists now call a geological weapon. Evacuation at this scale has never been attempted in Europe. Roads leading away from Pozzuoli and western Naples number fewer than a dozen major arteries, all of which pass through choke points and tunnels. The math is brutal. Even under perfect conditions, moving 900,000 people requires 72 hours. But the ground had one more secret. Dr. Christopher Kilburn from University College London has monitored Campi Flegrei for decades. His team's 2023 study confirmed what many feared. The caldera is approaching rupture. Our new study confirms that Campi Flegrei is moving closer to rupture, Kilburn stated in Nature Communications. However, he emphasized, this does not mean an eruption is guaranteed. Dr. Giovanni Chiodini from INGV added another dimension. His research suggests magma beneath Campi Flegrei may be nearing critical degassing pressure, the point where dissolved gases separate violently from molten rock. This threshold behavior creates explosive conditions. Once triggered, the system could transition from dormant to catastrophic in hours. Both scientists agree on one critical point. Previous predictions have been exceeded. The caldera's behavior now falls outside historical patterns observed during the 1950s, 1970s, and 1980s unrest episodes. What came next shocked even the scientists. Ground uplift at Pozzuoli has reached 1.46 meters since 2005, measured at the Rione Terra monitoring station by INGV's GNSS network. For context, that's nearly the height of an adult human. The rate accelerated from 10 millimeters per month in 2020 to 20 millimeters per month in early 2024, then spiked to 30 millimeters monthly during peak periods in early 2025. Recent data shows the rate has stabilized around 15 millimeters per month, but the cumulative stress keeps building. Each month adds another 1.5 centimeters of strain to rock already near failure.
Earthquake activity tells the same story. More than 1,000 tremors per month strike the caldera, many too small to feel but all contributing to fracture networks spreading beneath Pozzuoli. In May 2024, a magnitude 4.4 earthquake, the strongest since monitoring began in 2005, forced evacuations and damaged dozens of buildings. Carbon dioxide emissions from fumaroles at Solfatara crater now exceed 4,000 tons per day, according to INGV geochemical monitoring. For comparison, some actively erupting volcanoes release less gas. But Campi Flegrei isn't erupting. The pressure has nowhere to go. And the signs were already spreading. The system works like a pressure cooker with a welded lid. Beneath the caldera, multiple interconnected magma chambers hold molten rock and dissolved volcanic gases at temperatures exceeding 800 degrees Celsius. Above them, a caprock of solid stone, fractured by millennia of stress but still intact, seals everything below. As magma heats the overlying rock, gases try to escape, but with no release valves, pressure accumulates instead. The ground swells. Earthquakes multiply as rock fractures under strain. Each unrest episode weakens the caprock further, bringing the entire system closer to what scientists call coordinated failure potential. This isn't gradual release. When the threshold is crossed, multiple weakened zones could rupture simultaneously. The entire caldera would behave as a single explosive unit, detonating across kilometers rather than venting through a single point. But this was only the beginning. Scientists tracking ground deformation patterns noticed something disturbing in 2021. Between periods of rapid uplift, the rate of subsidence changed. Instead of fully relaxing after each stress cycle, the crust retained more accumulated strain. Each episode left the rock weaker than before. Dr. Stefano Carlino from the Vesuvius Observatory confirmed the pattern. The intervals between major unrest periods are shortening. The 1950s episode lasted 2 years. The 1969-1972 crisis ran 3 years. The 1982-1984 event spanned 2 years. The current unrest phase, beginning in 2005, has lasted over 2 decades without full resolution. The feedback loop is accelerating. Microfractures created during one cycle become pathways for gas and fluids during the next. Heat weakens rock that was already damaged. Pressure that once dissipated through slow deformation now focuses on fewer, more critical fracture zones. In 2017, Kilburn's team published their progressive approach model showing Campi Flegrei is evolving toward conditions more favorable to eruption. Their 2023 update confirmed the prediction. The caldera continues moving toward what they describe as explosive culmination. The timing remains uncertain. What scientists know is the direction, toward rupture, not away from it. What the ground did next was terrifying. Historical records from 1538 provide the only modern reference for what Campi Flegrei can do when it erupts. For decades before that September, the ground rose sporadically, reversing centuries of subsidence. New land emerged from the sea near Pozzuoli. Residents dismissed the changes as curious but harmless. Then came the earthquakes. In spring 1534, tremors rattled the region. They continued intermittently for 4 years, growing more frequent as September 1538 approached. On September 28th, about 20 tremors struck between dawn and nightfall. That night, the sea near Tripergolae began boiling. Fish floated dead to the surface. At 7 p.m. on September 29th, the ground exploded. Frito-magmatic detonations, where rising magma contacted seawater, blasted rock and ash skyward. Pyroclastic density currents, superheated avalanches of gas and volcanic debris, swept across hundreds of meters in seconds. Within 12 hours, a new volcanic cone, Monte Nuevo, had grown where a village once stood. The eruption paused for 2 days. Residents, believing the worst had passed, climbed the new mountain. On October 6th, a final explosion killed 24 people on the slopes. By October 7th, Monte Nuevo stood 123 meters high. The entire village of Pergolae and its ancient Roman thermal baths lay buried beneath volcanic rock. But the danger was far greater now. In 1538, fewer than 50,000 people lived in the affected area. Most were fishermen and farmers scattered across coastal settlements. No major infrastructure existed beyond dirt roads and wooden buildings. Casualties from the week-long eruption totaled dozens, not thousands, because people could simply leave.
Today, nearly 1 million people live on Campi Flegrei's roof. Pozzuoli alone houses over 75,000 residents in densely packed apartment blocks. Naples International Airport handles millions of passengers annually. The port of Pozzuoli moves thousands of tons of cargo weekly. Highways, fuel pipelines, electrical substations, and hospitals cover ground that was farmland in 1538. The same precursors are present: decades of uplift, accelerating earthquakes, rising gas emissions. But the consequences would be incomparably worse. A modern eruption matching 1538's intensity would encounter fuel storage facilities that could ignite, chemical plants that could release toxic clouds, tunnels and bridges that would collapse under pyroclastic flows. Casualty estimates for even a moderate eruption exceed any European disaster in recorded history. The difference between 1538 and now isn't the volcano's power, it's what humans built on top of it. And the volcano had one more warning. Satellite thermal imaging from the European Space Agency detects synchronized heating across the caldera floor, not isolated hotspots, but coordinated temperature increases suggesting connected pathways beneath the surface. Earthquake swarms recorded by INGV seismometers form geometric patterns, clusters along ring faults that trace the caldera's ancient boundary. These aren't random tremors, they're organized fracturing events. The crust is breaking along predictable lines, concentrating stress where the caprock is thinnest and the underlying pressure is highest. Multiple monitoring agencies, including ESA, INGV, and international volcano observatories, detect identical warning signatures. In February 2025, a seismic swarm beginning at 3:53 p.m. local time produced 450 earthquakes in less than 48 hours. The largest, magnitude 3.9, struck twice in separate locations, suggesting fracture networks are propagating laterally across the caldera. By March 2025, a magnitude 4.6 event, the strongest instrumentally recorded at Campi Flegrei, caused structural damage in Pozzuoli and forced temporary evacuations. Ground deformation maps show the caldera floor rising in a radial pattern centered on Pozzuoli. The uplift isn't uniform. Some areas rise faster than others, creating differential stress that bends and cracks bedrock. Where the ground pulls apart, pathways open for magma and gases to rise closer to the surface. Every data stream points the same direction, toward coordinated failure. But this was only the surface story. When the caprock finally fails, there will be no warning lava flows, no gradual buildup of ash. The system operates on binary logic, sealed or ruptured. Once the threshold is crossed, explosive energy releases instantaneously across the caldera. Supersonic pyroclastic flows, clouds of superheated gas and rock fragments moving faster than sound, would race across the landscape at speeds exceeding 300 kilometers per hour. Temperatures inside these flows reach 800 degrees Celsius, hot enough to ignite wood on contact and boil water in human tissue. Urban areas within 10 kilometers would be reached in under 10 minutes. Pozzuoli, sitting at the caldera's center, would have no time for organized evacuation. Bagnoli, Agnano, and parts of western Naples would face similar timelines. These aren't estimates from computer models, they're calculations based on flow dynamics observed at similar calderas worldwide. The eruption column would rise 18 kilometers into the atmosphere according to volcanological simulations, injecting volcanic ash into jet stream altitude. European air traffic would halt immediately. The Mediterranean's busiest flight corridors would close. Electrical storms generated by ash particle collisions would disable communications infrastructure across southern Italy. What came next was even worse. Naples International Airport sits less than 15 kilometers from Solfatara crater. Pyroclastic flows traveling at highway speeds would reach the runways in under 15 minutes. Every aircraft on the ground would be destroyed. The terminal, built to handle mass evacuations, would be engulfed before buses could even load. The port of Pozzuoli, directly above the most active seismic zone, would be annihilated in the opening seconds. Fuel storage tanks along the waterfront would detonate, sending fireballs across the bay. The resulting secondary fires would overwhelm any remaining firefighting capacity. Highways through the red zone funnel through narrow passes and tunnels. When pyroclastic flows struck, the heat would cause instant structural failure. Tunnels would collapse, bridges would fall, roads would disappear under meters of volcanic debris. The transportation network designed for evacuation would become a death trap. Industrial facilities in the Neapolitan suburbs store chemicals, pressurized gases, and explosive materials. Once ignited by pyroclastic flows, they would create cascading disasters. Toxic clouds, additional explosions, fires that burn for days. The urban landscape itself would become a secondary hazard. Emergency responders, already overwhelmed by earthquake damage and mass evacuations, would face infrastructure collapse on every front. Power, water, communications, fuel, all failing simultaneously within minutes of the initial detonation. But the disaster wouldn't stop at Italy's border. An 18-kilometer ash column would ground European aviation for days, possibly weeks. Ash particles, sharp fragments of volcanic glass, destroy jet engines on contact. Every flight path across the Mediterranean would close. London, Paris, Frankfurt, Barcelona, thousands of flights suspended. Economic losses would climb into billions within hours.
Mediterranean supply chains would fracture immediately. Shipping lanes through the Tyrrhenian Sea would become hazardous. Ash fallout contaminates cargo. Ports close for cleanup. The flow of goods between Africa, Europe, and the Middle East grinds to a halt. Electrical storms generated by volcanic ash create electromagnetic pulses that disable sensitive electronics. Communication satellites passing through the ash cloud could suffer permanent damage. Ground-based networks would face cascading failures as relay stations lose power and connectivity. Acid rain, formed when volcanic sulfur dioxide mixes with atmospheric moisture, would fall across southern Europe and North Africa. Agricultural regions in Sicily, southern Italy, and coastal Tunisia would face crop failures. Water systems would require extensive treatment to remove acidic contamination. The continental consequences would unfold over months: food shortages, displaced populations, economic disruption measured not in millions but billions of euros. And yet, officials had no solution. Ideal evacuation protocols require 72 hours of advance warning, time to mobilize buses, open shelters, clear highways, and coordinate the exodus of nearly 1 million people. But explosive volcanic systems don't provide 72 hours. Historical precedent suggests hours at best, possibly minutes. Emergency planners face a binary decision model: evacuate everyone immediately based on uncertain precursors, or wait for definitive signs and accept casualties. False alarms carry political and economic costs. Missed warnings carry human costs. There is no safe middle ground. During internal discussions, officials quietly acknowledge the concept of acceptable losses. Not publicly, never in press releases, but in closed meetings the question arises: how many casualties become inevitable when evacuation is physically impossible, when 900,000 people must move through a dozen exit routes in under an hour? The mathematics are brutal and unforgiving. Even if every vehicle were pre-positioned, every route clear, every resident cooperative, the physics of mass movement through constrained infrastructure cannot be overcome. Someone will be caught by the pyroclastic flows. The only question is how many. Maria Conte lives on Via Fasano, 3 blocks from Pozzuoli's waterfront. At night, she feels tremors through her mattress, some weeks 2 or 3 a day. Her children ask if the volcano is waking up. She tells them the scientists are watching, that warnings will come in time.
But late at night, after the children sleep, she stands on her balcony looking towards Solfatara crater. Steam rises from fumaroles in the pre-dawn darkness. The smell of sulfur drifts through the streets. She knows the evacuation routes, she's read the maps, and she knows that when the moment comes, the roads will be jammed with everyone else who waited too long. "We watch the news," she says quietly. "We check INGV bulletins. But what can we do? Leave our homes every time there's an earthquake? This is our life. This is where we live." Her apartment, purchased with 2 generations of savings, is now worth half its 2020 value. No one buys property in the red zone anymore. Maria and her family, like hundreds of thousands of others, have no choice but to hope the volcano stays quiet a little longer. For the first time, European volcano monitoring agencies are aligned. INGV, ESA, and international observation networks all confirm the same conclusion. Campi Flegrei represents an unprecedented threat to regional stability. No comparable European volcano carries this combination of explosive potential and population exposure. The reclassification as a national security threat marks the first time a volcano has received this designation on the continent. Continuous satellite surveillance tracks every millimeter of ground deformation. Automated seismic arrays analyze thousands of earthquake signals in real time. Gas sensors monitor emissions at 1-minute intervals. The scientific consensus is clear. Traditional emergency planning is insufficient. The timeline between definitive warning and catastrophic failure may be too short for conventional evacuation. New protocols are being developed, but they remain untested and controversial. Officials privately acknowledge that some level of disaster mitigation rather than prevention may be the realistic goal. The question shifts from stopping the eruption to minimizing casualties during a crisis that could unfold faster than response systems can handle. Similar mechanisms may exist at other supervolcano systems worldwide. Yellowstone in the United States, Long Valley in California, Toba in Indonesia all show signs of pressurized magma beneath intact cap rocks. Explosive preparation could be occurring undetected beneath other populated regions. Campi Flegrei is becoming a case study for understanding supervolcano behavior before eruption, but no one can control the forces building beneath Naples. There is no engineering solution for a volcanic system this size, no way to drill relief vents through kilometers of fractured rock, no method to cool magma or release pressure gradually. Monitoring provides data, data informs decisions, but decisions cannot stop geological processes that began long before humans arrived. The recognition is sobering. Some threats exceed human capacity to mitigate. The best science can offer is observation, measurement, and warning. How society responds to those warnings, how quickly people move, how effectively infrastructure holds, those factors determine survival. The focus has shifted, not from preventing the inevitable, but from saving as many lives as possible when it happens. Every earthquake swarm provides data to refine eruption forecasts. Every ground deformation measurement improves rupture models. Every simulation of pyroclastic flow paths help emergency planners identify the most critical evacuation corridors. The scientists monitoring Campi Flegrei understand something the public doesn't. The clock is already ticking. Is this Europe's first supervolcano awakening in real time? The data suggests yes. Can pressure release safely through slow magma withdrawal and gradual deflation? Scientists remain uncertain, but historical precedent is not encouraging. Could evacuation ever succeed with only hours of warning? The honest answer is no, not for everyone. Campi Flegrei's classification as a national threat means the Italian government acknowledges what scientists have quietly understood for years. The system is approaching rupture. The question isn't whether the caldera can erupt again, but when it will and how many people will be in the way when it does. Over 500,000 people live directly above the fractured caprock. 6 million more live within reach of the consequences. The volcano's power hasn't changed since 1538. What changed was what we built on top of it. And now, for the first time in nearly 5 centuries, Campi Flegrei is showing signs it's ready to break through again.